In Chapter 8, we're going to look at the chemistry of acids and bases. Now, we have encountered acid-base reactions in the past. For example, we saw that we could take something like hydrochloric acid and react that with a base like sodium hydroxide, and the product of that reaction, or products I should say, would be water plus sodium chloride. Now I'm going to show the reaction in a little bit more detail. Okay, where we have the bonds actually being shown here. So we have the HCl reacting with the sodium hydroxide, where we can see the bond between the sodium and the hydroxide. Of course, remember this is going to be an ionic bond. Okay, and the product, I'm going to show this kind of color-coded here. Okay, so you can see here where things came from and where they went to. And what we notice here is that the whole crux of the reaction, it all comes down to this hydrogen right here. This is what makes an acid-base reaction an acid-base reaction. Okay, we have the transfer of H+. Now, when we talk about the transfer of H+, sometimes we refer to this as being a proton, which sounds a little bit strange because a proton is a subatomic particle. But when you think about it, a hydrogen atom is going to have one proton and one electron. So you take away that one electron, you have a proton. So H+ is really just a proton. Okay, so every acid-base reaction is going to involve this transition, this transfer of a proton from the acid to the base. So now what I'm going to do is I'm going to write this out in slightly more general terms. Okay, where I'm going to write HA as being kind of the general formula for an acid. Okay, that's kind of the requirement for an acid, is it has to have an H. Okay. Now, for the base, the way I'm going to generalize the base is by showing something with a lone pair of electrons and a negative charge. It doesn't necessarily need to have the negative charge, but many of them do, especially in the case of hydroxide. Hydroxide has a -1 charge. So you can see what's going to happen here is the transfer of the proton to the base, leaving us with whatever's left over from the acid, which will be negatively charged, usually. Okay, now we have some terminology here. The thing that has the proton to start off with is what we call the acid. Okay, the thing that is going to accept the proton is what we call the base. The thing that is formed as a result of the acid-base reaction, in other words, the thing that that contains the proton that's been transferred, is called the conjugate acid. And the thing that's left over after the proton is left is called the conjugate base. Okay, so we can say that HA and A- are a conjugate acid-base pair. Okay, so if we were to look at something like HCl, its conjugate base is going to be Cl-. Okay, or if we're looking at something like HNO3, it would be NO3 minus. Okay, these are all conjugate acid-base pairs. The thing that we need to remember here is that in order to figure out what the conjugate base is, all you do is you take away one proton and then you make the charge one more negative than it was. So, for example, if we consider something like phosphoric acid, okay, right now the phosphoric acid is neutral, so we're going to take away one of the protons, so this becomes H2PO4, and since we removed one proton, it now has a negative charge. So that's a conjugate acid-base pair. But we could also look at what the conjugate base of this acid would be. Okay, again, we remove one proton. Okay, and we make the charge one more negative. So right now it's a -1, so it becomes a -2. Okay, so those would be a conjugate acid-base pair. Likewise, HPO4 with a -2 charge has a conjugate base, which is PO4 with a -3 charge. Okay, so that allows us to predict what the conjugate base of a particular acid is going to be. Okay, now, when we're talking about acids and bases, what we're going to find is that we can categorize acids and bases as being either strong or weak. So we can have a strong acid or a weak acid. Okay, and the difference between the two is how readily they give up a proton into solution. So for example, if I had a strong acid, and a strong acid would be something like HCl, if I take that and I add it to water, the HCl is going to dissociate into H plus and Cl minus ions and then react with the water. So the water, remember, has a lone pair of electrons, actually two lone pairs. So what we've wind up forming here is hydronium as the conjugate acid plus chloride as the conjugate base. Okay, and here's the thing. With a strong acid like HCl, every single molecule is going to break up. So in other words, once you add the HCl to the water, instantly all of it becomes this H3O plus, which we call the hydronium ion. Okay, and that's what we would expect for a strong acid. Now, there's a number of different acids that do this. There's actually 6 of them. Okay, so those strong acids are HCl, HBr, and HI. Okay, that's 3 of them. Those are based on the halogens. So notice chlorine, bromine, and iodine all show up in group 17 of the periodic table. What's glaringly missing here is fluoride. This is a common mistake people make, but hydrogen fluoride is not a strong acid. That's not to say it's not dangerous. It's actually some of the nastiest stuff out there. But HF does not completely 100% dissociate in water. So therefore it's not a strong acid. Okay, the other 3 are perchloric acid, HClO4, nitric acid, HNO3, and sulfuric acid, H2SO4. Okay, now I do want to point out that for sulfuric acid, there's 2 acidic protons there, but only one of them is strongly acidic. Now, as far as weak acids go, the way that they work is very similar to what we have with the strong acid. So let's use HF as our example since we know it's not a strong acid. Now if I take HF and I react it with water, okay, it's going to produce hydronium plus fluoride. You might think, well, that looks exactly the same as HCl. Well, there's one big difference here, and that is that this reaction is actually reversible. Okay, so at any given time, once you have added the HF to the water, there's going to be some HF still laying around. Okay, and that's what makes it a weak acid. So we have the 6 strong acids, and all other acids are weak. So really all you have to do is memorize the 6 of them, and then anything else would be considered a weak acid. Now we can also have strong bases and weak bases. Okay, so, oops. Okay, a strong base is a lot like a strong acid in the sense that it completely ionizes. So a strong base would be sodium hydroxide. Well, if I add sodium hydroxide to water, what's going to happen is we are going to get ionization. So we're going to produce hydroxide ions in solution. Okay, plus the counter ion. Okay, so every single molecule of hydroxide gets converted over, every molecule, or I should say every formula unit of sodium hydroxide gets converted to hydroxide. Now, a weak base does not produce hydroxide in solution directly. Okay, instead what's going to happen is that weak base is going to steal a proton from water. So for example, ammonia, NH3 with its lone pair, okay, is going to react with water and produce hydroxide plus ammonium. Okay, but again, this is going to be a reversible process, so the reaction's going back and forth. So at any given time, there's going to be some of this ammonia laying around and some of this ammonium laying around. Okay, so we have strong acids, strong bases, and weak bases. Okay, you need to be able to identify those when you see them. Now, one thing that's kind of interesting here, you might have already picked up on this, is that when we're looking at the reaction of the weak acid with water, okay, we see that water is acting as a base, okay, accepting that proton. Whereas in the other reaction down here, water's giving up its proton. In other words, it's acting as an acid. So how can it be both? And what effect does that have on the properties of water? And that's what we're going to look at in the next video.